Hello everyone. Today we're going to discuss why to learn Verilog. We're going to discuss some combinational design examples, both done through hand using logic design techniques and implemented in Verilog. So first we should start off with why to learn Verilog. Verilog is a computer program here that allows you to create a file called a source file to describe a digital circuit. So Verilog designers, they create digital circuits through writing code in here, and then that code gets saved in a file. And then with that Verilog file, you upload it to either an FPGA, like this one, or you can take it and have that Verilog file be created into an ASIC. An ASIC is in phones, in tablets, in calculators. There's going to be many ASICs, digital ASICs, and the humanoid robots that come out in the future. So, and all of those are made with Verilog. So there's a massive incentive to learn Verilog if you're a computer or electrical engineer. And this playlist is going to be aimed towards teaching you from start to finish how to go from a beginner to an expert in Verilog. And for some resources, there is this textbook, Introduction to Verilog with Vivato. Actually, it's just Introduction to Verilog. So, let me find it. This book will explain all the fundamentals of logic design and the fundamentals of Verilog-based design. This book, it's aimed with its target audience being students. So it goes over all of the different kinds of problems that a university will ask you. And if you're a student with me in Digital Design 1 here at UTSA, all of your test problems are going to come from this. So and if you're not a student and you're just here at UTSA and you're a student at a different university in, I don't know, Oklahoma, the probability, and you're taking a computer engineering course in digital design, learning logic design, then they're probably going to ask you the same exact things as all of this. Because this was written with the intent of covering all possible combinations of things they can ask you in these courses. But in this playlist, we're not going to go over all of this because this is just how the universities like to test people. These are the problems they ask. In the real world, you only need around 20% of all of this to build very robust systems, and the rest of it is just redundant. And in this video, I'm going to show an example of two examples covering the most important parts of the combinational design section. So to start, a combinational circuit, let's begin with that. So, where is it? So, a combinational circuit is a circuit whose outputs update instantly the minute you change the input. So in this circuit, and all combinational circuits can be thought of as a mathematical function. So they take in inputs, in this case it's A, B, and C, and will output X and Y. when A, B, and C are 0, 0, 0, we get 0 for x, 1 for y. So if we do that, 0 for x, 1 for y. And we make C1, they both are 0. We make B1, x is 0, y is 1. We make them both 1, both become 1, the outputs. So that's how it is. And it changes instantly. So when I change B, in this case, 1, 0, 1, they're both 1. And then 1, 1, 1, they're 0. So when we toggle, it changes instantly. So that's what a combinational circuit is. It's something that changes instantly. Like its outputs are automatically updated when the input changes. That's all a combinational circuit is. And every combinational circuit can be represented in a table. Some of the tables are too big to write by hand, but they are still technically can be in a table if you were to just spend an eternity specifying all possible combinations. But in this example, we're going to go over the ones that are small and that can be modeled in a table, which is a large portion of the combinational circuits that matter. Okay. Okay, so in this example, this is the same example I showed you previously with the outputs updating instantly in that simulation. This is how you would do it by hand in logic design. If you, for every time you have a table here, if the table has 3 inputs, A, B, and C, you will use this structure, this thing, for each output. So there's X, so we make one for X, and there's Y, we make one for Y, and it's usually empty. Here, I should probably just do one from scratch so you can see. Let's do one from scratch just so you can see the process. So every time you have a table that has 3 inputs, you create one of these. Okay. So this is, oh darn. So this is 0, 1, 3, 2, 4, 5, 7, 6. So for the x1, for the 0 column, 0 row, x 0. So this 0 goes there. So for here, when x is 1, when the row is 1, x is 0. So 0. When it's 2 and 3, it's 1, 1. From here. Wait a minute. Hold on. Sorry. According to the book, it's actually this. Hold on. What am I doing? 0, 1. 0, 1 goes there. 1, 1 goes there. 2 is 1. 3 is 1. Okay, so 4 is 0. 5 is 0. 5 is 1. 0. So this is, so it's going to be BC A. So then okay, so every time we have a truth table that has 3 inputs, we make this kind of K-map for it, and the index of the row determines the location where its output gets recorded in the table. So this is how an example is. Here, for index 0, we take d equals 1 and put it there. When it's 1, we move, that's a 0. 2 and 3 are 1. That. So when we use that approach here, when x is 0, move a 0 there. When x is 1, when the row is 1, 0 there. The rows 2 and 3, it's 1, 1. The rows 4 and 5, it's 0, 1. And then the rest are this. Now we circle them. And then from that, we get an expression for x, where x is equal to a b prime c plus a prime b. And the way this was derived is this term corresponds to this one, and this one to this one. And the way that is because in this circle, a is constant, but it's always 0, so it turns to a prime. And in this one, b is constant, it stays 1 here, 1 here. C changes from 1 to 0, so C gets dropped, but B was always 1, so it stays as B. In this one, all 3 terms are constant, so not a single term gets dropped, but A was always 1, so it's A. B was always 0, so it's B prime. C was always 1, so it's C. And then we're able to get this equation. And in this previous solving of it, we use different kinds of K-maps, but even if you have a different K-map, you can still get the same answer if you just use a different methodology where you can write the numbers in, not with the indexes, because this K-map will have, it's going to have different positions here because the A, B, and C are different. But even without that, if A and B are 0 and C is 0, we take x is 0. So there. A and B are 0, C is 1, 0. Anytime A and B are 0 and 1 respectively, we get 1. So you can map it out that way. But the faster way is to just take the table, know that this is the K-map you use with these numbers always fixed, and then copy the value from its respective row in. And what else is there? Oh yeah, and this shows you how to extract the terms in a very predictable fashion. Okay, so that's how you would do it by hand. Now I'm going to show you how to take. Okay, so hold on. Okay, so I just showed you how to make this portion. like this whole thing for x, and then you do this. You would have done the same to get the y expression, and then you physically build the circuit. But now we're going to go over how to do it in Verilog. Hold on, let me look up. Let's go to the start. So, in logic design, to design a combinational circuit by hand, you have to make your K-maps, you have to create your equations, like with this. But in Verilog, you can use what's called a behavioral approach to describe the circuit at a high level and have it implemented instantly. So this is an example of how that's done. But let me just do it. So in our circuit, our inputs and outputs all go in the top here. So A, B, C, X, and Y, we defined them all. Okay. So there's that. Then if you want to implement the truth table directly, you just do this. Always at star and we do if what on earth? And y equals so what's going on? Okay. So here we have our truth table, and we just defined row 0. If A, B, and C are equal to 0, 0, 0, 0, 0, 0, X and Y is 0, 1. And if we do that for the rest of them, get this. Let's see. This one was 0, 0. Okay, so this truth table is implemented here. We got our, when there's 0, 0, 0, we got 0, 1. When it's 0, 0, 1, we got 0, 0. When it's 0, 1, 0, we get 1, 0. When it's 0, 1, 1, we get 1, 1. When it's 1, 0, 0, we get 0, 1. When it's 1, 0, 1, we get 1, 1. When it's 1, 1, 0, we get 0, 0. And when it's 1, 1, 1, we get 0. Hold on. Let me make sure it's all right. Get 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, Okay. So now that we have this, that's literally how you implement the entire digital circuit. So you can take this Verilog file and put it on an FPGA immediately. Or you can make an ASIC such that when A, B, and C are given a voltage of either 1 or 0, the output pins will reflect the exact behavior described by this table. So if we had a chip, we make A and C attached to the input of, I don't know, a 5-volt battery, and then B is tied to the negative end, so ground. X and Y are going to be 5 volts, because that's what the table explains. And if we take this Verilog file, we can make that chip. So, and now let's go over how to make a test bench. To make a test bench, to actually make sure your circuit is behaving how you want, you need to simulation sources, create simulation source. I like to call it test bench, because it's a test bench we're going to make. And the best way of making a test bench is actually to just use ChatGPT. Because, I mean, making source files, it's good to use your brain for that, so I don't recommend ChatGPT for that. But for test benches, there's just really no point of hold on, let me just do it quick. There's just really no point of doing that yourself. So let me bring it up. So make a test bench for this. So let's make it instant. It's so easy for it. Maybe it'll do that. Okay. Now let's run the simulation. Okay, so this is how it's simulated. Well, we're simulating A, B, and C, and X and Y. At this first time, all of them are 0. So X is 0 and Y is 1. At the second time, A and B are 0 and C is 1. So it's this case, 0. And if you look, all of this will match the behavior of this table. So we know that our circuit was created correctly. So that's how you design this Verilog file for a combinational circuit. And let's say we had a bigger table. Like, let's say we had 4 variables. We had A, B, C, and D. You just do this. And then it's still X and Y, you just specify it all. And then you just make all the rows underneath. And just use the same approach. Okay. But yeah, that's done. And I guess Well, I'll actually show you how to deploy this exact circuit on the board. So what you need to do is make a constraint file. So this constraint file here allows you to map the inputs and outputs to a physical pin in this board. So the switches are obviously, that's going to be where we set our inputs. So let's make switch 0, A, switch 0, B, switch 0, C, and then let's say we want, so we mapped in, we have these mapped into switches, hold on. So this right here, this first switch, that's A. The second one, that's B. This third one, that's C, because that's how it's mapped. And then let's make X equal to the first LED and Y equal to the second LED. How can I show this? I need to point carefully. So right now, this switch here is A. This one is B. This one is C. So we map the inputs. Now let's map the outputs. Well, we're going to make this LED here X and this one Y. So this one's X and this one's Y. Then you do that. And then once you have your source file and your constraint file, then you just click generate bitstream. And then we wait. And because I'm going to actually put in the effort to edit this, that time is going to go by like this. Alright, we are back now, and the bitstream is generated up here at the top. So now we go to Hardware Manager, click Open Target. Oh, one important thing. It's important that this part be selected. You pick that at the start, but you only pick that part if you have this board. Okay, but anyway, that's done. So click Open Target. You can either do it here or here. I'm just gonna do it this way. I like it this way more. Then you click Auto Connect. Then what on earth? What? Oh, it's not connected. Hold on. Let me plug it. It wasn't even plugged in. Okay. So this right here is the thing. We just uploaded it onto the board. So hold on, let me bring up the other one, the better table. So right now, let me bring it closer. So right now these three switches are 0. So these three switches are 0, as you can see. So only Y is 1. If we make C switch C1, the outputs will turn to 0. So let's do that. Switch C becomes 1, so then they're both going to become 0. And if we make B1, so we can go back, and then we're going to make B be 1. Then now X is 0. If we make both B and C 1, then both X and Y are going to be 1. So A, B, C. C. So it is following the exact behavior of the table, where these first three switches are A, B, and C, and these two LEDs represent X and Y. And this switch is A, this switch is B, this switch is C, and then I think that one's X and that one's Y, because that's how we mapped it in the constraint file. So, yeah. So we have created from start to finish a combinational circuit of our choosing as modeled by the table, created a Verilog file for it, and implemented it on an FPGA. If we had thousands of dollars, we could make a chip to implement that exact behavior and have it be mass produced. And while it might be pointless to do that for this simple circuit, you can do this process that we did for any digital circuit. You can design it to do, instead of having it be implementing this table, you can have it implement a neural network to do AI on a chip. You can have it do arithmetic. You can have it do signal processing. You get to choose what your Verilog file is. It's just that for this example, we made a very simple one. But there you go. In the next lesson, we'll discuss sequential design, and we'll go over the basics of that. Thank you.